This is the first part. I have to VCC 5 voltage positive power supply, and I have 4 switch here, and I have 2 resistor, and also 2 LED. It will show the output result, and here is the pull down resistor. So for this JK flip flop, the true table is if J is 0 and K 0, it's no change, and J is 0, K is 1, Q is 0, it will be reset. If J is 1 and K is 0, Q will be 1, and it's set. If J and K are both 1, it will be toggle. And also you can see I have 1% here, and I also have a clear here. So when they are in a high level, like when they are in a high active state, if percent is 1, and the output Q will be 1. And if the clear in a high state, and the output Q will always be 0. So if I run the circuit, you can see that. So I didn't close the other switch. I only closed the one connect to the clear. So you can see, so it's now in a high state. The output Q is always 0. And if I open the switch and I close this one, you can see the high state in the side, and the Q output always be 1. Also, I will show you this one. So the table is here. You can see that if the percent is 1, then Q is 1. And if clear is 1, the Q will be 0. And the other things, they will follow the true table. This is the second part, and I add a clock here. Key clock signal in the JK flip-flop circuit is the clock input that triggers the flip-flop to evaluate its input and potentially change its output state. So how the clock signal controls the output Q? Um, I will show you example here. Like here is a clock signal, and on the rising edge, like here, here, and here, 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 and here. So we can use the table here. The first one, like D is 0 and Q is 0. Q is 0 here, and here D is 0, so Q is 0 in this period of time before the second rising edge. And here D is 0, D is 0 here, so Q is 0. And here D is 1, so Q is 1. And here D is 0. And he go back to 0. Here is 1, this one, also this one. So the last of time they're all 1. So this is how the clock signal control the output Q. Here is the third part and function generator. It acts as the clock source for the first flip-flop, and I also have another one flip-flop, and I have 3 LED here. They will show the signal for output. So when I run the circuit, you can see first LED is flashed in the frequency of the function generator, and the second one and the third one, you can see the frequency of the second one and the third one is special because they represent the binary counting sequence, and the flip-flop changes state with each clock pauses. The LED turn on and off to display a binary number, with each LED representing one bit of the binary output. And the function for this circuit is to demonstrate a series connection of JK flip-flop, commonly used in digital circuits for various applications, including counters and shift register. And for the flip-flop, it acts as a frequency divider, having the frequency of the clock signal, and the second flip-flop divides the frequency further. This is the last one, and if I run the circuit, you can see these 4 LED all flash in a special sequence. So, so it is the binary count sequence, and if each LED represents bit, with the leftmost flip-flop being the least significant bit, and the rightmost being the most significant bit. The sequence will present a binary count from 000 to 111. So in decimal it's 0 to 15. And the function for this circuit is it acts as a binary counter using JK flip-flops. Each flip-flop represents a binary digit, and the combined state of the output, like these 4 LED, they are represents a binary number, and the counter increments its binary value on each clock pulses. And here is the waveform for the output A, B, C,